Hi, video on the multiple choice you did a couple of weeks ago when I was off sick. Okay, I think it's worth going through this, so let's go. If you've got any other questions, please ask me, but this is the one you did a couple of weeks ago. There'll be one this Wednesday as well on equilibrium, okay, just to make sure you understand things. So here we are, the Haber process, the manufacture of ammonia, represented by this equation. Which statement is correct about the equation when the temperature is increased? Both forward and backwards rate increase. That is always true. Forward rate will increase, backward rate will increase. They won't increase by the same amount, but they will both increase. So that's obviously the answer. Okay, that's rubbish, and that's rubbish. There's no effect on the backward rate. Well, that's rubbish, isn't it? So the answer is 1A. Number two, swimming pool water can be kept free of harmful bacteria by adding aqueous sodium chlorate. This reacts with water to produce the HFCl molecules, which kill bacteria. There you've got an equilibrium, first of all. This is an equilibrium, as you can see. And the second one isn't an equilibrium. All right, so because of that. Bright sunlight, the OCl minus is broken down by the ultraviolet light, and we get this. Okay, we get oxygen and chloride ions. Which method would obtain the highest concentration of HFCl? So we want the highest concentration of this. So we want this equilibrium to shift this way. Acidify the water. Well, if we acidify the water, what would that do? It would react with the OH minus ions in this reaction. H plus OH minus will give us water. And so if I acidify the whole thing, my hydroxide ion concentration will decrease. If this, because of this reaction here, if this decreases, this equilibrium will move to the right, and we'll get plenty of this stuff. So that looks like the answer to me. Let's check the others to make sure. Add a solution of chloride ions. If I add chloride ions, that's not going to do anything because this isn't an equilibrium. So that's wrong. Add a solution of hydroxide ions. Well, that will increase this rate backwards, won't it? And that will decrease my HOCl. Where else are we? And bubble air through the water. Well, this is air, effectively, isn't it? This is the only thing that's like air. And that won't do anything either because it's not an equilibrium. So the only answer I can see is 2A. All right. Excuse me. Given the following enthalpy changes, that and that, what's the standard enthalpy change for the formation of iodine trichloride? I think I've done this one, but never mind. Where are we? The standard enthalpy change of formation. So let's draw it first. Let me get a nice different color. So ICl3. Okay, that must come from I plus Cl. They must be in their standard condition, so it's I2 and Cl2. And they're both going to be, this is going to be a solid, and this is going to be a gas. Now we've got to balance it, so half of one of those and 3/2 of that. It's balanced now. This is now delta H formation of ICl3 solid. Okay, so how am I going to make that from these two guys? All right, now looking at the first one, I solid must be on the left. So I want this as it is because I solid is on the left. So I'm going to leave that as it is. Okay, and that's going to be plus 38. This one, I want, there you go. I'm going to add this one straight away. I want Cl2 on the left. Okay, so I'm not going to do anything, am I? I'm not going to change this at all. So add that plus 3 Cl2 gives 2 ICl3, and that's minus 214 up there. Now I've got to add these two in such a way, this one and this one, to get this. Okay, so if I add them at the moment, what will I get? I'll get 2 ICl3s, and I only want one. So I'm going to divide the top one by 2. So I'm going to say half of that. Is that right? Yeah, half of that. I'm going to say 3/2 of that, and I'm going to say one of those. If I halve that, this halves. It was 214, so that's going to be 107 now, isn't it? So it's minus 107 because I've halved the quantities. Now, this one at the bottom, I want half of I2 here, don't I? So I'm going to times this one by a half as well. Half of that and half of that. Half of 38 is 19. So this one is plus 19 now. Let's add these two together. What do I get? Use a different color. Right, the half I2 gas is going to cancel with the half I2 gas there. I'm going to get half I2 solid. That's that one sorted out. plus 3 over 2 Cl, which is that one sorted out, and it's going to give me ICl3, and that one sorted out, so it's going to give me this. So I halve them both and add them, and let's have a look at that. So, God, my brain's going. So I'm going to add 20 to minus 107. That's minus 87 minus 88. I hope there's an answer there. There you go. That's 3B. Any questions, please give me a shout, and we'll do them a bit more in detail. Organic nitrates in photochemical smog can cause breathing difficulties. Diagram shows an example. What's the correct bond order? 1, it's sp3 hybridized. So 1 is 109.5. 4 electron directions there. Number 2 is sp2 hybridized. So that's 120, isn't it? 2 is 120. 3 looks like 180, but it's not because there's 2 lone pairs here. It's actually a tetrahedral, which is 109. Chop off 2.5, it gives me 107. Chop off another 1.5, it gives me 104, I think. Or 2.5, we chop off, don't we? So this is going to be 104.5, something like that. All right. So which one is smallest first? Which one's the smallest? 3 is the smallest. Then 1, and then 2. So the answer is C. Hope that one makes sense. If it doesn't, give me a shout and I'll redo it. This one looks very straightforward. Enthalpy combustion. Here we are. We've been given combustion data, and we've got to find the formation of this thing. So I'm going to rewrite it. 4 carbons. I'm going to ignore the state symbols just for quickness. C4H10. All right, I'm combusting these. So if I combust this, I get 4 carbon dioxides. If I combust 5 hydrogens, I'll get 5 waters. And if I combust this must be the same. I'll get the same stuff. All right, so which one do I want? Let's pick a nice color, that color. This is the one I want, delta HR. I'm going to call this one delta H1 and this delta H2. From Hess's law, delta HR is equal to delta H1, there's an R by the way, delta H1 minus delta H2. Okay, what is delta H1? Well, it's 4 combustions of carbon, which is minus 394, plus, all of this is square brackets, plus 5 hydrogens, which is minus 286. Okay, all of that is delta H1 minus delta H2, which is the combustion of butane, which is minus 2877. Okay, that's the sum. Because my calculator is disappeared. I'm going to have to use the one on the computer, which is awful. All right, 394 times 4 is equal to 15, whatever that is. All right, and now I'm going to take away from that minus 5 times 286. 286 gives me that, and now I'm going to add 2877, and I get minus 129, so the answer is B. If you don't understand that, please give me a shout. I'm going to pause the video now to get the next 5 up, if I can. Oh, there we are. Okay, so here's number 6. The value of the equilibrium constant Kc for the reaction to form ethyl ethanoate is 4. Now this one's quite a nice one actually. All right, so when 1 mole of ethanol, there's 1 mole of ethanol, reacts with 1 mole of ethanoic acid there, they're allowed to reach equilibrium. What's the number of moles of ethyl methanoate formed? So at the start we've got none of that and none of that. And now we've got to do something tricky kind of thing. Okay, let me rewrite this, C5OH. I'm going to say plus the acid gives us the ester. That's water. So it starts, we have 1 mole of that, 1 mole of that, none of that, another that. So this is at the start. And at equilibrium, well, let's pretend we get x of that and x of that. And so we're going to have 1 minus x of that and 1 minus x of that. So there you go. These are the concentrations at equilibrium. This method, you've got to learn this method, by the way. It's a very common method. All right, now if I draw my Kc, all my colours the same, let's pick that colour. Kc is equal to the concentration of the ester times the concentration of water divided by the alcohol times the concentration of the acid. And as you can see, Kc has no units. Okay, so we can just use moles directly. So ester times water is x squared, isn't it? According to this, over 1 minus x squared. Okay, now we could solve this using plus or minus b, square root, whatever, but we don't have to. All of this equals 4, as you can see there. And so we can solve this very easily by rooting both sides. So square root of this is equal to the square root of this. So root of 4 is 2, is equal to x over 1 minus x. So let's cross multiply. 2 minus 2x is equal to x. Therefore, 2 is equal to 3x. All right, I think. And therefore, x is equal to 2 over 3. And there you go, b. Okay, I hope that makes sense. That's a tricky one. As I say, there's a method to that one, so please learn that one. Number 7, what statement describes the halogens, chlorine, bromine, and iodine? Their bond energies decrease with increasing bond energy, proton number. So what's the bond energy? So we start off with chlorine, then we have bromine, and then we have iodine. And bond length increases going down, so the bond energy will decrease. So that looks good to me. So I'm going to say 7A. Their first ionization energies increase with increasing proton number. That's not true, is it? The electron you're removing is further away, and therefore it's easier to remove. They're all coloured? No, they're not. Well, they are all coloured, but they're not all coloured gases. They're good reducing? No, they're not good reducing agents. They're good oxidizing agents, but they're not good reducing agents. Okay, so the answer is A, 7A. Excellent stuff. This number 8. Which diagram correctly represents the Boltzmann distribution on molecular energies at two temperatures, T1 and T2? T2 is hotter, so it's going to be shifted that way. So, and the maxima is going to decrease. So let me draw what I mean. If this is T1, something like that, T2 will look something like this. The maxima will be lower, but it was shifted to the right. So not only is the maxima lower, it's also shifted to the right. So this looks reasonably good. This is wrong because T2 is higher than T1. This is wrong because T1 is on the right. It's shifted to the right. So these two look T1 and T2. Now I don't know why they do this, but they look very similar, don't they? Okay, so what's the answer here? All right. I'm going to say it's going to be this one because it's got to start off at 0. Right? We have very few numbers here. Here it's saying that all of them, 0 molecules have this energy, and that's not right, is it? So the answer is B there. Okay, it's a bit of a weird one, but there you go. This one, I love this question because this is proper chemistry. This is deductive reasoning. Okay, table gives the radii in picometers, and picometer is 10 to the minus 12 meters. So of these, so these are the radii of these ions. All right, cesium chloride, which is this one, has one type of lattice, and sodium chloride has another lattice. Sodium chloride and magnesium oxide have this lattice, but cesium chloride has this kind of lattice. We don't really have to know the lattice names, but one of them is called face-centered cubic, and the other one is hexagonal close packed. All right, which factors appears to determine the type of lattice? The charge on the cation. Well, the charge on the cation here, cesium, is plus, but here it's sodium is plus, and magnesium 2 plus. So the cation charge doesn't mean anything, does it? Because the cation charge on this one and this one is the same, and yet they have different structures. So it can't be that one. The ratio of the ionic charges, well, this is 1 to 1, but sodium chloride is 1 to 1, and they're different structures, so it can't be that. The ratio of the ionic radii, let's have a look at the ratio. Cesium chloride, cesium is 167, chloride is 181. All right, let me get my calculator out so I can give that a number. 167. Actually, I'm going to do it the other way around. Oh no, it doesn't matter, does it? Divided by 181. Oops, that's messed up big time. 167 divided by 181. So the radius, the ratio there for this guy is about 0.92. All right, let's do the sodium chloride and the magnesium oxide. The sodium chloride, 102. Chloride is 181. So this is for cesium chloride. This one is for sodium chloride, and this one's going to be for magnesium oxide. Magnesium is going to be 72 divided by oxygen, 140. Okay, so the ratio for sodium chlorides is going to be 102 divided by 181, and that's 0.56. Much smaller, that might be interesting. And magnesium oxide, 72 divided by 140, and that's 0.51. 0.51. So these are quite close to each other and they've got the same structure. So the thing that determines the structure is the ratio of the ionic radii. So that one looks good to me. The sum of the ionic charges, that doesn't mean anything, does it? The sum here is 2, I guess, plus 1 minus 1. The sum is 2. And here it's 2 as well. So the only one that we can show that gives us different structures is C. I hope that makes sense. I really do. All right, methanol can be prepared by the reaction between carbon monoxide and hydrogen. There you go. The relevant bondage is given. What's the interchange of the reaction? This is pain, only because it takes ages, and it's not hard. It just takes ages. 2H2 gives me methanol. All right, we've got to break that. We've got to break 2 of these. And then we've got to make this. Okay, so what do we break? We break that. So that's going to cost me 1077 plus 2 into HH, which is 436. And all of that equals 2 times 436 plus 1077. 1949. 1949. So we've got to break everything there, and we're going to make 3 CHs. The CH is 410. All right, we've got to make a CO, which is 360, and we've got to make an OH, which is 460. Excuse me. And so that is 410 times 3 equals that, plus 360 plus 460. 2050. All right. So enthalpy change in the reaction is the bond energies of the bond energies of the reactant minus bond energy of the product. Excuse me 1 second. And that gives me where's my thing? Okay, make that minus, add it to 1949. 1949, and I get minus 101. There you go. So I get that. Woo, that was effort. All right, so I think I'm done. Yeah, let me get the next 5, and I'll be back in a minute. This one is number 11. Which solid has a simple molecular lattice? Calcium fluoride is ionic. Nickel is metallic. Silicon oxide is giant molecular. And sulfur is simple molecular. So the answer is 11D. Here we are. Reaction pathway illustrates the energies of reactants, products in the transition state. Which expression represents the activation energy? Activation energy is this. So it's E1. Whoops, E1 minus E2. That number minus that number gives this. E1 minus E2. There you go. That's the activation energy for the Ford reaction. This one is hard to see. I don't know how you manage this. A dimer X, I think it says that. Yeah, I think this is a dimer X is stable when solid, but in a dynamic equilibrium with is set up in solution. So its X goes to 2Y. Solution X has initial concentration of 5, so X goes to 2Y. Solution has initial concentration of 0.5. Okay, when in equilibrium it's reached, it's fallen to 0.25. So at the start it's that, and this is 0.25. If 0.25 go over, this is 0.5, isn't it? Because it's 1 to 2, and 0.25 of this has reacted, and that's going to give 0.5 of the Y. So these are the numbers we've got to look at. Okay, changes in X are plotted until equilibrium is reached. So X must start at 0.5, so that's possible, that's possible, that's possible. And of course, they all look possible. So they all look good. Okay, that's annoying. Now, where does Y end up? Y ends up as 0.5. So this is not possible. This one's not possible. Y is 0.5. This looks good. And Y, Y looks good here. So that looks possible. Oopsie daisy. That looks possible as well. So this one looks possible, but then I forgot where does X end up. X ends up at 0.25, and that looks about 0.25. So this looks good here. And this one is 0.25 as well. So this one looks good. So the answer is either C or D. Okay, now we've got to find out what Kc is. Kc is equal to concentration of Y squared divided by the concentration of X at equilibrium. So the concentration of Y is 0.5, so it's 0.5 squared divided by 0.25. Okay, so what's that going to give me? Whoops, wrong button. So we have 0.5 squared, 0.5 times 0.5 is equal to that, divided by 0.25. And I get 1, so this is the answer. So it's not that, the answer is C. Hope that makes sense. If anything doesn't make sense, just drop me a line and I'll figure it out. In aqueous solution, the acid HOI disproportionates according to the following equation, where M, N, P, and Q are simple whole numbers in their lowest ratios. The equation can be balanced using oxidation numbers. What are the values for N? So all we need is this one and this one. All right. So, excuse me. So we've got HIO goes to I2 plus HiO3. So let's have a look at the oxidation numbers here. Nice color change. I'm going to use blue. So oxygen is -2, hydrogen is +1. So iodine here is +1. Iodine here is 0. Iodine here is -6, +1. So this must be +5. All right. Now from here to here, it goes -1. And from here to here, it goes +5. So there must be 5 of these compared to the other ones. So if that's unless I've, oh no, it's not +5, it's +4 because it goes from +1 to +5. So it goes up by +4. So this must be, I'm making a mess of this, aren't I? This must be 4 of those to 1 of those. So in total, that means we're going to have 5 H, this guy. It's going to give 4 I2s plus 1 HOI3. Okay, that's how it's going to work. Okay, because it's got to go down by 4 units as it goes up by 4 units. So 5 of them, 4 of them go down by 1 unit, 1 of them goes up by 4 units when this reacts. So I believe this is N and this is P. So N is 4, and P is 1. So there you go. The answer is C there. Hope that makes sense. If it doesn't, give me a shout. Different Boltzmann distributions are shown, that and that. In diagram 1, one curve, P or Q corresponds to a temperature higher than the other curve. So obviously Q is the higher temperature. So it's one of these two. In diagram 2, one line X or Y corresponds to the activation energy for catalyzed reaction. Catalyzed reaction is going to be less. The activation energy is going to be less for a catalyzed reaction, isn't it? So the presence of a catalyst is X, so it's going to be this one. So it's going to be C. Hope that makes sense. Again, if you don't understand, give me a shout. Student puts 10 cc's of 0.1 mol of sulfuric acid into a test tube. Oh, could be confusing, this one. All right, there's a test tube, and inside I put 10 cc's of 0.1 molar of sulfuric acid. All right, into a test tube, and 10 cc's of 0.1 molar ethanoic acid into another test tube. Oh, great. So we're going to put 10 cc's of ethanoic, and I think, the concentration is the same, 0.1. All right, he then adds 1 gram, an excess of magnesium rim. So we're going to add Magnesium ribbon to this one. There's a bit of ribbon, and then ribbon to this one. Okay, are we good? Yeah, both acids have the same starting temperature. Neither reaction is complete after 2 minutes, so they're both going on, but both are complete after 20 minutes. Oh, that's a bit useless, isn't it? Now, which temperature is greater? After 2 minutes, the sulfuric acid is a higher temperature than the ethanoic acid. That's going to be true because after 2 minutes, all right, this is going to be a faster reaction and more energy is going to be put in the water because H2SO4 is a strong acid. Okay, so that's going to be true. The sulfuric acid is going to be hotter. After 2 minutes, the sulfuric acid has produced more gas than the ethanoic acid. Yes, that is going to be true because more of it is going to be produced in 2 minutes than the ethanoic acid. After 20 minutes, the sulfuric acid has produced more gas than the ethanoic acid. That is going to be true as well because you might have the same number of moles of acid, okay, but you don't have the same number of moles of hydrogen ions because sulfuric acid is diprotic. In other words, it forms 2 hydrogen ions. But ethanoic acid only forms 1 hydrogen ion. So you've got double the number of hydrogen ions. So you'll get double the amount of gas. Now, why does that happen? Well, because the 1 gram is in excess, so you'll get more gas produced with the sulfuric acid. I hope that makes sense. I hope I've got it right as well. I think I have. Which statements about covalent bonds are correct? Triple bond consists of 1 pi and 2 sigmas. That's wrong. It's 2 pi's, isn't it? And 1 sigma. So that's wrong. The electron density in a sigma bond is highest along the axis. That is true. So it's between the molecules, isn't it? So there's a sigma overlap. It's along this axis, isn't it? So that's true. Pi bonds restricts rotation. That's true because the way they overlap each other is like that, and rotation is hard because if they rotate, the bond is broken. So that's true. So the answer for that one is C. Oh, by the way, if all 3 are correct, like in this one, number 16, the answer is A. Okay. Number 18, which type of intermolecular forces can exist between urea molecules? Hydrogen bonding, yes, because that will hydrogen bond with another molecule. So you'll get something like this. All right, and then you'll get an interaction between the hydrogen and the nitrogen. So that is possible. Permanent dipole. Yeah, there's a dipole there, isn't there? There's also other dipoles. So there is a permanent dipole there. So you will get those. And these van der Waals forces, yes, you'll also get those. You'll get those all the time. So the answer is A there. All right. Number 19. Was that the last one? No, number 20 is. Diagram represents the Boltzmann distribution, molecular energies at a given temperature. There it is. What are the factors that affect the rate of reaction can be applied using this? Increasing the concentration? No, that doesn't tell us anything because this is an energy diagram. So that is not true. Increasing temperature, you can say that because you can draw another one of these. So that, and the addition of a catalyst, yeah, if you know where the activation energy of the catalyzed reaction is, you can tell something about the rate of reaction. So the answer is 2 and 3 only. The answer is C for number 19. And last of all, here we go. Ethanol is manufactured by something or other here. Ethene and steam, the presence of phosphoric acid. There it is. Reaction is carried out at 570 Ks and 60 atmospheres. What would be the consequence of carrying out the reaction at the same temperature, but at the pressure of 200? So we're increasing the pressure from that to that. So increasing the pressure is going to force it this way, isn't it? The manufacturing costs would increase. Yes, pressure is expensive. Expensive. So if you can get away with low pressure, you get away with low pressure. Maximum yield at equilibrium would be higher. Yes, because it would shift to the right. So that's correct. Reaction would proceed at a fast rate. Yeah, it would, because you're squishing the molecules together and they're going to interact more often. So the answer to that one is going to be A. All right, let me stop this now and then post it.